Hello.
Yes, we can hear you. You can start.
Okay. So the presentation is on screen. You can see the presentation.
Yes, we can.
Sorry.
We can.
Okay. So hello everyone. I'm Dr. Shagufta, and thank you very much for joining our first technical webinar. So this is in picture. This is ICORR leaders. In middle, you can see Dr. Yunan Gao, who is now president of Institute of Corrosion, and in left, Dr. Anthony. He is now vice president of Institute of Corrosion, and in right, Stephen Ted is immediate past president. And we have 4 trustees and 20 council members, and the Institute of Corrosion is governed by all council members. Here you can see the structure of Institute of Corrosion. Institute of Corrosion has several branches and divisions: Corrosion Science Division and Corrosion Engineering Division. Corrosion Science Division and Corrosion Engineering Division. And Institute of Corrosion has many more evenly distributed branches in UK and in overseas. Uh, CSD Corrosion Science Division closely work with university, uh, and it organizes conferences, and it gives many awards in corrosion science and corrosion engineering. The chair of CSD is Julian Wharton, and CED, Corrosion Engineering Division, is mainly industry focused. Institute also has Young Institute of Young ICOR, that is Y-ICOR. So Y-ICOR gave opportunity to young professional for networking. Now, history of Institute of Corrosion. So uh, British Association of Corrosion Engineers was established on 21st May 1959 in London. So British Association of Corrosion Engineer is now Institute of Corrosion. Mission of Institute of Corrosion. The mission of Institute is corrosion is promote science, technology, and ideas about corrosion through formal education and training. It develop and support global community of corrosion experts, and it influences policy and decision making, and it creates sustained and healthier and safer environment. It promotes career development and networking. Now I hand over to Dr. Arpit Goel, who is chairman of ICORR India branch.
Yeah. Thank you, Shagufta. So first of all, on behalf of ICORR, it's my pleasure to welcome you all to this session. So today makes a significant milestone as we officially launch the ICORR India branch. I believe it's a step forward in fostering innovation, collaboration, and excellence in the field of corrosion science and engineering. To begin with, I would like to acknowledge the unwavering efforts of ICOR's leadership, particularly our current President Yunan and immediate past President Stephen, for their invaluable support and guidance in making this branch a reality. In addition, I also extend my thanks to our position holders whose vision and dedication have been instrumental in this endeavor. So let me take a few moments to introduce our team behind ICOR India. So myself, Dr. Arpit Goel, I am currently assistant professor at Thapar Institute of Engineering Technology. I'll be the branch chair. And Dr. Shweta Goel, she will be the vice chair. She is a professor at Thapar Institute. Dr. Shagufta, she will be the secretary external. She is the editor of ICORR UK. She will be the secretary external. Dr. Prasanna, he is assistant professor at IIT Tripati. He will be the secretary internal. And Dr. and Jayaprakash sir, he will be the event coordinator. He is CEO of Corsac India. So in addition to this launch, we are privileged to host an engaging technical session today. Our esteemed presenter is Dr. Professor Paul Lambert. He is a renowned figure in the field of corrosion with over 40 years of experience in investigating structural durability and degradation, as well as developing novel remedial techniques for civil and building structures. Paul has left an indelible mark on the industry. Most recently, he is serving as a head of materials and corrosion at Mott McDonald's and became one of the three inaugural Mott McDonald's Fellows in 2023. He's also a visiting professor of the Center of Infrastructure Management at Sheffield Hallam University, where he leads groundbreaking research into novel materials and repair technologies. In fact, Paul is one of the first person whom we contacted to put us in contact with ICOR UK to start this plan. So thank you, Paul, for the initiation. Today, Paul will share his insight on 200 years of CPA and OPC. So, as we know, this year 2024 marks the 200 anniversaries of both Cathodic Protection in January and patenting of Portland cement in October. One or both of these transformative technologies have played major roles in development of the modern built environment. This is a fitting moment to celebrate these bicentennials, reflect on their impact, and explore this future trajectory. I believe this webinar reflects ITO's commitment to advancing knowledge and fostering meaningful exchange within the corrosion community. I'll encourage everyone to actively participate, ask questions, and engage with peers. So once again, thank you all for joining. And without further delay, I would like to invite Paul to please start his session.
Thank you very much. I've got a presentation, so I'll see what I can do about sharing it.
Yeah.
Now, let's see if this is going to work. I think that may be working.
Yeah, we can see that.
And I'll put it on the presentation proper. There we are. Can you see that okay?
Yeah, we can see that.
Excellent. And also, hopefully, you can hear me.
Yeah, we can hear you. Yeah.
Thank you for inviting me. I mean, I'm genuinely very pleased to have been invited. It's a great honor to be involved in this very important startup of what I think will be one of the more important branches that we will have as we actively enlarge the institute. It's tended to be a little bit inward facing for the last 50 years. And I think now, partly because of better communication, such as we're using here, there's been the realization that we don't need to be so insular. We should spread our wings and all benefit from the basis of that. However, I am not here to plead a case for cooperation. I'm here to give you a little bit of insight and hopefully tell you one or two things you didn't know about, and maybe tell you one or two things you did know about, but in a way you haven't heard before, concerning two very important areas for me, certainly, of cathodic protection and ordinary Portland cement. On the right, there's a fairly modern viaduct. I say fairly modern, it's old enough to have problems because it's not only made from OPC reinforced concrete, but the little grey boxes you can probably see on the top of the crossheads are actually part of a cathodic protection system. So it's, however new it is, it's already benefiting from both of the 200-year-old technologies I'm going to talk about today. In fact, it may be more appropriate to perhaps antiquify the whole thing because let's face it, we're talking about 200 years ago. I've put the old logo for what used to be the Institution for the Cathodic Institution of Corrosion Science and Technology, ICORR as it used to be. For some reason, a lot of the bodies in the UK suddenly decided that institution sounded a bit old-fashioned and changed the names to institutes. Personally, I like the old name. I like the old logo. And in fact, it still appears on official documents and forms. So if you get a certificate, there's a very good, you will get the old logo with the vine leaves and very, very grand indeed. The bridge there now, instead of the more relatively modern concrete bridge, that's actually the new old London Bridge. It's the one that eventually got sold to America, but replaced the one that was famously always falling down in songs. Despite the fact that one of the verses in the songs says, build it up with iron bars, and the following verse goes, iron bars will rot away. So even over 200 years ago, there was an awareness that marvelous though iron and steel was, it might have limitations in certain applications. Don't worry, I'm not doing the whole thing old-fashioned. We'll go back to, not quite now, but recently. I thought it might be useful to have a little bit of background on me. Why would you want to know? Should you know anything about me? No reason at all. Why should you? Maybe it's best if you know who the heck it is who's talking here at the moment. There we are. That's when I started with Mott MacDonald, 1989. Brave, eh? Cover meter survey on a reinforced concrete column. As you can see, I'm toting all the current 1989 safety gear. I've got my high impact kicker boots. I've got my high vis fisherman's jumper and my fall resistant hair. If I was seen doing that even a year after this photograph was taken, I'd be marched off the site and possibly arrested. Just to make it better, you'll see I've got my heels bang up against a drop of unknown depths. Feel free to use this photograph if you ever need to bring to attention the fact that people are not using the PPE, the personal protective equipment they should be doing. But it was sort of normal in those days, wrong though it might be. I think the assumption was if you're smart enough to have worked out what the heck you're doing there on the site in the first place, you've probably got enough brains not to fall down a hole. It's very easy to say that. All I had to do was step backwards to contemplate my handiwork, and well, I wouldn't be given this presentation. Move forward a few years, in fact, further back a few years. This is 5 years earlier. Look, no beard. I think I'm wearing the same shirt, by the way. Isn't it wonderful being a student and the like? But yes, I've been messing with steel. I've been messing with concrete for a very long time. Again, I've got my safety trainer shoes on there. And the idea is if I drop the concrete, I can run away quick enough for it not to land on my feet. I'm also apparently showing off my digital watch, which I was really proud of. I got it for my 21st birthday. Great watch until I ground the face of it off while preparing a metallurgical sample. Who said we're in a safe industry? It can cause all sorts of damage. We'll come a bit more modern though, in a sense. There we are. That's more like me now. I'm the one on the left, for those who are not sure. The one on the right is one of 100 cast iron figures of Anthony Gormley, who is a sculptor. You may know him for the Angel of the North, which is a huge aircraft wing-sized figure that's at the top end of the M1 going into Newcastle in the northeast of the country. He's got 100 of those, and why we stood there? Well, it's not a bad photograph, is it? But it's more than that. The idea is that we share a lot. We've both come from the ground, really. We're made up of material that's come from the earth, and in time we will return there. How long we last will depend on a number of factors. How well we're looked after, whether we're given appropriate protection, whether we're given a job that is suitable for us. If we mistreat either of those figures, they won't manage the 100 years. Well, the cast iron will manage 100 years. I don't know. I've gone more than 3/4 now, so I'm hopeful that I've got a fighting chance. But other than that, we'll see. But the statue should do it. But iron, except when it appears as a meteor from space, and then it is rare and sold for huge amounts of money or put in museums, it's not natural. It's not a natural material on this planet. It is artificial. You could argue that iron and steel are as artificial as a plastic bag. They're only here because we put a lot of effort into making them. And that energy is easily lost as they return to a more stable condition and return back to the earth. So a lot of what we have to do in terms of corrosion control is about fighting nature. A happy fight, a nice fight, a pleasant fight, and a very worthy fight, but it's nonetheless, it is a fight. It's not, we shouldn't blame a piece of steel for wanting to rust. It's only natural. If we think about the year, Let me just see if I can get rid of a little thing on my side here I want to get rid of so I can see what there we go. No, I'm not. Well, I do wish it had stopped being helpful. Never mind, we'll ignore that. The wonders of presenting halfway around the world. 1824, yeah, last year was the 200th anniversary of 1824. Why was it important? Well, January the 22nd happens to be my birthday, by the way. No hints, don't worry. Humphrey Davy, he was then president of the Royal Society, published a paper on the corrosion of copper sheeting by seawater and methods of preventing this effect. And in fact, that was the first paper that really described the mechanism that we know of as cathodic protection. And while sometimes it's misreported as having been to do with stopping steel corroding, it was originally copper that they were interested in. It was the copper holes on the ships. They had problems with steel, with iron and steel combined, particularly with copper and put in seawater. We'll see about that in a second. But it was about copper that most of this was to do with. Now, just to put it in context, the same year, later the same year, there's the Mechanics Institution was established in Manchester, northwest of England. That is now Manchester University. So Manchester University, what was for a period UMIST, both came out of the Mechanics Institution. In fact, the Metropolitan Museum of Manchester also came out of that organisation. So that was very important because that was one of the first universities that it was not Oxford and Cambridge based. It was not London based. It was in the industrial north and opened up the option for training, education, and general development in that time. Lord Byron, famous weirdo poet, he died in the same year. That sort of puts it in context. He had very strange individual. He's buried all over the place. I've seen two places his bits of him are buried. I don't know what it was at that time. It seemed to be the fashion. Some of it's buried in Rome in the non-Catholic graveyard. I think his heart is somewhere else, and it's anybody's guess where they distributed the rest. Now, Beethoven premiered one of his Symphony No. 9. Good grief. That really dates it, doesn't it? You've got the same year, Lord Byron dies, Beethoven releases one of his famous symphonies. And the other thing I put on there is Royal Society for Prevention of Cruelty to Animals, RSPCA, was formed in the UK. Lots of other things happened. One thing I haven't put on there was there was a contentious American election with both sides being horrible to each other and bringing the whole mechanism of the USA presidential elections into disrepute. But as that would never happen again, I haven't bothered listing that one. I mean, that's clearly was a one-off 200 years ago. At the bottom is the second main point, which is Joseph Aspdin. He was a bricklayer from Leeds, and he patented a material he called Portland cement. It wasn't absolutely unique, but it was a particular formulation of a known type of hydraulic cement that suddenly became, as indeed, far more popular than he could have ever imagined. Was one other event, by the way, that predated these. I'll just mention this. Humphrey Davy, he had a laboratory assistant called Michael Faraday. You may have heard of him. And as it turns out, he finally got elected to be a member of the Royal Society, which meant effectively he was officially allowed to go and work where he worked and get paid for it. There was only one vote against him. Some suggest it was Humphrey Davy who was trying to stop him getting in, but Humphrey Davy himself is very, very clear on the matter that it wasn't. But never mind, Michael Faraday, you could argue in many ways, probably became, if not more famous than Humphrey Davy, certainly more significant with respect to his understanding of magnetism and currents and generation of power, electromagnetism, eddy currents, all sorts of things. So finally, he is seen to be there. This is just the sort of evidence of those two statements about it being there, being 1824. The one on the left is the first page off the paper that's in the Royal Society's journal. You can get that. You can find it online. It's not a great read, but it's there. And it does actually go on to say, you know, this could be really important. I mean, even at the bottom of here, it says, it promises to illustrate some obscure parts of electrochemical science and likewise seems to offer important practical applications. And indeed, it certainly has. Though initially it was just for the copper holes. On the right, there is the 1824 patent for what you'll notice is not called Portland cement, but it's called artificial stone. And that's how it was originally sold. Why Portland? Well, it was certainly nowhere near where it was being made. It was being made in Leeds, up in the county of Yorkshire, in the north of England. It was called Portland cement because Portland stone was very popular at that time, but expensive. And if you mixed sea sand and especially with a few broken shells and a bit of seawater, and you mixed it in with some of the Aspin's special grey powder, it made something that looked exactly like Portland stone. Well, it's close enough anyhow. So it was originally sold as an artificial stone mix, but it has remained essentially unaltered in the 200 years since. Joseph Astor himself, quite rightly, is honoured in his in Leeds. There is a plaque on the wall, and it recognises the fact that Portland cement's one of mankind's most important manufactured materials. I mean, sometimes it is treated with less than honour on the basis of carbon dioxide emissions, but that's hardly Joseph's fault. I think we can honestly say none of us would be exactly where we are today if it wasn't for Portland cement, because I know the floor I'm on is concrete, and I'm sure many of you are in structures that have got concrete floors, concrete frames, and certainly without concrete, we would not have been able to build the infrastructure on which we all so rely in any sort of way that we have. I'm sure somebody would have come up with something else. It's so important, of course, it's in an important location. And so there it is. It's remembering the person associated with one of the most important manufactured materials of all kind. And it's over the waste bins at the back of a nightclub in Leeds. So if you're ever in the centre of Leeds, you can find it. It's there. You'll be one of the few people who's seen it sober. You'll be one of the few people who've seen it probably standing up, but that's where it is. There is a move at the moment to try and get it relocated somewhere a bit more honourable, but it's proving hard to do. We'll see how it goes. At least hopefully the plaque, and like the cement, will last longer than the nightclub and its waste disposal system. I'm not going to say a great deal more about Portland cement now, because really there's enough to be saying about cathodic protection, and that goes that's probably closer to what we're interested in as the Institute of Corrosion. I acknowledge that. I've got a little bit of a history. I mean, it's very Eurocentric. It's very UK-centric, inevitably from 200 years ago working on. But erosion, corrosion, the word corrosion first gets used by Boyle, he of Boyle's law. But he's talking about erosion, corrosion, that combination of sort of chemical loss of material with mechanical loss of material, where there is moving water, typically. So the word corrosion, which of course dates way back before it was ever used to mean what we think of it as in terms of a way in which metal is degraded and lost, was first used by Boyle. Bimetallic corrosion actually is much older than you'd think. It dates right back 1763. We'll have a quick look at that in a minute. Then we've got it quite a bit later, because those two are sometimes linked much more closely than they truly are. We're looking at sort of 60 years about before cathodic protection comes about. Cathodic protection is a consequence of an awareness of problems with the bimetallic corrosion, but it isn't directly related to it. We get things like inhibitive pigments, not so much being made as understood. They've been using things like red lead paint before 1919, but they didn't know why they worked. From 1919 onwards, it was understood why certain things worked to control corrosion as chemicals. And then that led to, obviously, development of much more effective additions to coatings, for example. Other things, intergranular corrosion of brass, famously came about by some of the wars in hotter countries, where they noticed that the shell casings of the soldiers were cracking, and it was partly the ammonia from the sweat, partly the locked-in stresses, but it was basically failure of brass because of the environment it was in. And then things like inhibitors come much, much later. The formal understanding of how corrosion inhibitors work is getting quite late on. As in everything. And that's clearly, as I say, UK-centric, but it covers quite a lot on that. Coatings themselves, of course, they go way back. From whether it be smearing ghee on an iron post or placing a highly designed synthetic resin with elaborately engineered pigments in them to get a 50-year life. That's been going. It's been an awareness for a very long time that if you put a layer of something between that which suffers an environment and the environment in which it is suffering, it's going to help. Let's put a thin layer of something in. Let's do coating. There we are. That's all I'm going to say about coatings. They think they're important enough, the coatings people. We're worrying about the CP people. It tends to break into two teams. Biometallic corrosion, like I say, goes back a long time. You can trace an awareness of it, a first serious awareness and a first serious scientific assessment of it to 1763 and a HMS Alarm. Now, it was basically one of the first ships that they tried out with a copper bottom hull. So they got copper sheeting nailed to the hull. They initially used iron nails, but very quickly realized that was a bad idea. As you start to understand how mixing different metals can work, you've got small areas of very corrodable metal linked electrically and in a continuous electrolyte with a huge area of a less corrodable metal, or indeed a noble metal and a base metal, and the base nails and the noble copper. That comes from Humphrey Davy. He first put the order in and called them base, where they were most likely to corrode, and noble, where they were least likely to corrode. But they noticed this. 1763, very quickly observed that this was a problem. They did some trials, and what they found was that when the copper sheets came, they came with waxed paper to protect the surface. So they would tend to just put that onto the hull of the ship, hammer it in with initially iron nails, and then tear the wax paper off. Now, where there was a little washer of wax paper that sat beneath the head, no corrosion occurred. So they were sort of getting a hint of how you're going to deal with it. Just separating the head from the copper, the iron head nail from the copper with some wax paper had great benefit in terms of stopping corrosion. But despite having spotted that, the conclusion from the Navy at this time was that you should never use iron in contact with seawater. Luckily, they changed their mind on that, or else one or two things would have been very different. At least the Titanic would have rotted at the bottom of the sea instead of rusting gently. But now for the time being, iron, oh, forget it. Don't touch iron. Having said that, they still made mistakes. So this is in 1763. Commodore Foul Weather Jack Byron sounds like the sort of person you'd like to trust your young son with to be a cabin boy. Foul Weather Jack, yes, he sounds like a good sort. But they went around the globe as you did in those days. And his copper bottom ship, the HMS Dolphin, that is actually an engraved. That is supposed to be HMS Dolphin. It's landing somewhere in the South Seas. It's liberating people of anything they can load on the boat and row away with. But at different times, different purposes. But they did report that every now and then they would hear the copper sheets on the bottom of the ship banging away because they were still using iron nails at that point. And every now and again, the rudder would drop off, which is rather nice. The rudder was covered in copper and had an iron pintle to rotate on. But because of the nature of it, the iron pintle would rot through and would fall off, and they'd have to go and make a new rudder, cover it in copper. It's funnily enough, of course, if they'd not bothered with the copper, it would have been okay. But the copper was there for a good reason. The copper was there to stop fouling and to stop burrowing worms, particularly in warmer waters, from going into the timbers. So the copper had its purpose and had proved to be very effective in terms of making the Royal Navy faster and more reliable on the whole. I just want to take you forward now to another ship of which I have a little bit more knowledge. This is pre CP, pre-cathodic protection, but it's after they changed over to using, they'd realized there was a problem with iron nails and they found a way of dealing with it. You can see the copper bottom on there. It's sort of painted a sort of reddy brown. This is the HMS Sirius. It was involved in some action off the coast of Spain. It was associated. It was part of the general melee that was occurring between the English, the Spanish, and the French at that time. And in fact, the ship sank. The HMS Sirius sank in 1810. So we know exactly how old it was when it went down and when the last time it was worked on was. Initially, the French thought that they'd sunk it and were very excited. And then it turned out it had been scuppered to block the waterway. So that was a dirty trick, wasn't it? But never mind. The important thing is that Sirius been at the bottom of the Mediterranean since 1810. And I was fortunate enough to have a colleague who was into diving. And they went down there legally with the paperwork, I am assured, and retrieved some pieces. These are from HMS Sirius. The copper sheet you can see, I don't know, if you look, you can probably see the little crow's foot mark on it, which means it was military. So that's the copper sheeting. There's one of the iron balls that the French would have been firing at the ship. Wouldn't want one of those landing at you, coming at you. Everything else you can see, apart from that ball, is copper. The nails, the small nails that hold the sheeting on, is copper. The larger ones, the big bolt, this whatever it is, they're all copper. They'd realized by then that if they used copper and they wrought it so that it became strong and hard, they could use it for the nails. And if they used copper nails with copper sheets, they didn't get the problem that they were getting with the iron nails. So the point I'm making here is that when Humphrey Davy came up with cathodic protection, it was nothing to do with iron nails. It was to do with the copper. Now, I think now is a good time to just think about cathodic protection. This is a bit of a cheaty diagram. The dotted line is for the most part, an either or. Though you can do both at the same time, and it's become popular recently. But if you think of that piece of metal, and it's in, don't care, water, seawater, soil, concrete, anything that's got a continuous moisture path, it is going to be potentially capable of corroding. In order to stop it corroding, the principle behind the cathodic protection is to add a separate anode, because the mechanism is that the anode, metal goes into solution, releases hydroxyl ions, releases electrons. The electrons travel through the electrolyte phase to the surface of the cathode. At the cathode, the electrons are combined with oxygen and water and make hydroxyl ions. It's not those hydroxyl ions will eventually react with the metal ions that are in solution and make what we think of as rust. But the important thing is that the element that is the cathode in that little battery, because that's what it is, doesn't lose material. Only the anode does. And that's exactly what was being looked at. They were looking at initially they used zinc, which continues to be popular. We now use magnesium and aluminium in different circumstances. They were also using pig iron, which is very, very, very rough iron. And that was working quite well as an anode for that galvanic side. Sometimes it's called sacrificial. Tends to be called galvanic now. Sacrificial has strange overtones. Galvanic is a more precise description of how it works. Of course, the thing is, the metal, all it knows is it's getting electrons. It doesn't know what's going on. It doesn't care that there's a piece of zinc sacrificing itself in the distance. So as long as we can get electrons to it, it'll be a cathode. It'll be quite happy. And we can do that with a power supply. It's only low voltage, few volts, relatively low current. The main thing is we need something that can throw that current without losing mass. And luckily, there are a lot of things that we can use. A very popular one these days is mixed metal oxide titanium. We also use titania. There are other ways, other materials that can be used as well. We want something that will not lose mass to any significant amount when it passes current. I said these are mostly an either or, but there are what tend to be called hybrid systems. What else? Everything's hybrid these days, but hybrid systems that are long-term galvanic but have an initial impressed stage, and you may well see those. They've been in use for a long time on marine structures, but there are systems that have been introduced, various types that can be used on, for example, reinforced concrete structures. The idea being that with the galvanic systems, there's less maintenance. The other way of looking at it is there's not a lot you can do once you've fitted it. It either works or it doesn't, and eventually the metal will be consumed. But more of that later. Let's go back to Humphrey Davy and Co. The first boat, the first ship, I guess, that they tried it on was the HMS Samarang. That is not the Samarang, that is the Trincomalee. It was its sister ship. The Trincomalee is in dock in a maritime museum in the northeast of England at Hartlepool. But I think you can see the copper. Shows how good that painting was, because that's what it looks like, that sort of browny red colour. A little bit of green there as well. That's got a copper bottom. That would have had copper nails, but the Samarang had what were these anodes fitted. They called them protectors. They fitted the protectors to the ship. It went off, it came back, it did what it was supposed to do. There was no weed, there were no shells, there was no barnacles. They didn't have to drag a cabin boy on a rope underneath to clean off the hole. It was perfect. The only trouble was when you start to put the protectors on and the copper stops corroding, that's not the case, because all of a sudden you're going to get weeds, you're going to get shells, you're going to get an awful mess on there. And the whole point of the copper was to stop those growing. So rather than, sadly, the Royal Navy, instead of recognizing this as being a success in terms of stopping things corroding, they saw it as a failure because it didn't, it prevented the copper from acting as an antifoulant. They had to eventually accept that, yeah, it's going to get consumed. So they took the protectors off. They didn't return for 100 years. And they also, which is unforgivable, allowed, in fact, encouraged the press at the time to make a fool of poor old Humphrey. And they did. They were encouraged to have cartoons of him. Here we have a cartoon of Humphrey's the person with the bellows in the middle. This is making fun of the sort of scientific meetings that would have at places like the Royal Institution, the Royal Society. They would usually put a small animal in a bell jar and suck the air out at some point. That was very popular. And they died, yes, but it sort of proved something. I think it proved people were entertained very easily in the 1800s. You can see Wellington up on the right. You can tell it's him because of his nose. But the aim was to sort of undermine the position of Humphrey Davy so that he looked a bit of a fool. They did worse, because one of the things that Humphrey Davy did, or rather didn't quite do, was he discovered nitrous oxide, laughing gas, but he didn't spot the link between laughing gas and using it for operations, for medical purposes. Laughing gas to him and his friends was a recreational drug, I'm afraid. Playing on that, other cartoons, for example, this one, that's Humphrey Davy in the middle, supposed to be, supposedly used it to, well, as it says here, living made easy, prescriptions for scolding wives. Yes, okay, well, he said, soonest mended. Look at the date, though, 1830. That's 6 years after, well, it'd be less than 6 years, probably about 3-4 years after the trials. So they were making sure that everybody thought of Humphrey Davy as a bit of a fool. In one respect, he perhaps did miss a trick. Despite the fact one of his friends at one of their laughing gas parties was so out of it that he burnt his foot off in the grate and didn't care. Nobody put two and two together and thought, you know what? This would be quite good if you got to saw somebody's leg off. It took a French physician another 18 months to realize that that was the case. And of course, laughing gas, nitrous oxide, is still used for medical purposes as anesthetic. Sadly, it's also still used by some people as a drug for entertainment, for recreation. But such is the nature, I'm afraid, of the humankind. So, what happened to CP? Well, initially, a lot of fuss. This is a little timeline I put together from papers that were published about the time, and you can see here that we've got a lot of activity around about 1820, lots of things being published. Then it goes quiet. Nothing happens. There's a little blip in 1860. That's actually Det Nos Veritas, who, like all good consultants, were claiming to be able to do things that other people didn't even know existed yet. So they actually talked about cathodic protection, though whether or not they knew what it was, we're not sure. But basically, they were publishing, they had documents out there sort of saying, hey, you know this cathodic protection from a few years ago? Well, if you ever want to use it, we're the people to help you. And then it went quiet again. And as you can see, it's basically 100 years before things start to pick up. And pick up they do, and they start to go. I gave up at 2000-ish. I mean, obviously, they're still very, very high. Lots and lots of interest in it. As its usage increases, its understanding of its usage increases, and the manners in which it can be used become more diverse. So what happened to Davy? Davy left England and put himself in a self-imposed exile in Switzerland. This sort of thing he did. And he died. He had a stroke at 50. He was a broken man. It's a great shame, but they succeeded in killing him off. This was somebody who had discovered aluminium, as he called it, but don't tell anybody from America that it was originally called aluminum. It then became called aluminium after a Scandinavian chemist produced quite a large amount of it, and then we've been arguing over it ever since. But aluminum or aluminium, he first person to isolate it. He improved on the miner's lamp, which is probably most famous in the UK, and of course the cathodic protection. And he was an important man. So Coleridge, the poet, wrote about Davy, his friend. Chemistry tends to turn priests into sacrifices, and sadly it's as true now as ever. 1 minute you're wonderful, the next minute you're a fool, and you're the same person. You did the same thing, but people choose to interpret it as they see best. I think it's jealousy, if you ask me, but sadly it carries on. However, if we go happier things, what about CP? Well, the boom in oil and gas in the US meant that there started to be thousands of miles of pipes going in. Initially, I don't think they cared if they leaked. Eventually, they realized, I don't think they were bothered about the leak, but they were bothered about the loss of product. So they wanted to look at what can we do to protect them? Well, when they're above ground, you can coat them, you can paint them, you can wrap them. When they're buried, it very soon became apparent that you could use cathodic protection. So that's what they did. And so 1920s, you're starting to see these problems, and you're also starting to get, in the 1930s, there are recognized systems for using mixtures of coatings and cathodic protection to protect these buried pipelines. And from there, it extends into so many other things. There's hardly a pipeline or a ship or an oil rig or anything like that, anything that's buried or submerged that isn't cathodically protected. You can't use it in the air, of course, unless it's in reinforcement in concrete. But basically, if you can see it, paint it. If you can't see it, CP it. That seems to cover most things. In the 1936, we got the Mid-Continent Cathodic Protection Association formed, which later became NACE, which I'm sure a lot of you are familiar with. And of course, NACE is now sort of becoming AMP, but everybody remembers NACE, and it's proving to be a difficult birth, I think, moving from NACE to AMP. But this is, it actually started as a cathodic protection body. I just want to show you in a little graphic cathodic protection of steel in concrete, because it works very well in concrete, because concrete's got a very nice environment in there. You've not got a free-flowing electrolyte. It's sort of held in a matrix, and that can have great benefits in terms of the effects that you get. When we're using steel reinforcement, using cathodic protection with reinforced concrete, in other words, combining these two 200-year-old technologies, what do we get? Well, this is, I apologize for the green steel. This is what happens when you move a perfectly good graphic from one PowerPoint slide to another one. PowerPoint routinely decides that that's not a good color. I'm going to give you a silly one. But let's accept that the turquoise bar with the pink writing, with the magenta writing is the steel, and the grey, brown, dotty stuff is the concrete. If corrosion is starting on there, we're getting anodes and cathodes being established. If that's happening, the reaction at the anode is the metal. As metal going into solution as an ion. So we're going to iron ions, as it were, and that involves the release of electrons. Those electrons will shoot along the metal to adjacent areas in these little batteries that corrosion is. And at the cathode, at the negative part, if you like, we've got oxygen and water and those electrons being combined to make hydroxyl ions. No loss of metal. No loss of metal whatsoever. Those hydroxyl ions will combine with the iron ions and eventually with more water and more oxygen and produce what we know as rust. But not necessarily where the metal is being released. The rust will go everywhere. If we put an anode, be it galvanic or impressed, onto or into this system, what we're effectively doing is we're swamping the anodes that already exist on the metal. And this is providing electrons to the steel. The steel's receiving electrons, it's cathodic. We do it right, that all of the steel becomes cathodic, so that the anode reaction is switched off. We only have the cathodic reaction. Great, we stop the corrosion, splendid. But that, as they say in the best adverts, is not all. We know that the main reaction we're going to get, the main product we're going to get is hydroxyl ions. Hydroxyl ions, alkalinity. Alkalinity is actually good for steel in concrete. We like alkalinity. Great, we're producing alkalinity. We're also, because the anode is positive and the steel is negative, we're also going to get anything that is negatively charged driven away. So chlorides will go away, sulfate will go away, and indeed hydroxyl ions will be pushed away. So the area around the steel, it'll be richer in hydroxyl ions, but they will be getting distributed, but it will be low in chloride and low in sulfates. And both of those are good things in terms of maintaining the condition of the steel. There are systems that are used specifically to increase alkalinity, sometimes called electrochemical realkalization, but you get it with cathodic protection anyhow. You can also optimize the chloride removal by electrochemical chloride extraction, but you get it with cathodic protection anyhow. The other thing that happens is in a field, electrical field, water moves and it moves away from the steel. You can get systems that just do that, electroosmosis, but you get it in cathodic protection. So that environment, that annulus around the steel very quickly becomes high in alkali, low in chlorides, low in water. Good conditions to maintain not only no corrosion now, but no corrosion if the system goes off for a while. So with steel and concrete, if the system goes down for a few months, frankly, it doesn't matter. It's not a matter of sending out a motorcyclist with the spare parts to repair and make sure it's working again. It's more a case of remembering to do something about it the next time you're out there. Be it 6 months or a year later, it probably doesn't matter once it's been operating for a while. As I say, it works incredibly well. Reinforced concrete. I'll just show you very quickly. I don't want to overrun, but I think just for completion, I'll show you a few systems. A lot of systems have been developed now for use in reinforced concrete, thereby combining both the OPC and the PC. We have meshes and ribbons. These are made from this coated titanium, mixed metal oxide titanium. The mixed metal oxide stops the titanium from anodizing. If we didn't put it on, the titanium would pass current very briefly, but then it would protect itself from an oxide layer, much as aluminium does. Excuse me. And as a consequence, it would stop passing current. By putting this mixed metal oxide layer on, it can continue to pass that current for a very, very long time. And it's available in all manner of different forms. Though those, the black and the blue plastic units are just clips that are used to clip ribbon, such as on the left, which is a small version of that on the right. Clip it directly to bars in new construction, because there is no reason on earth not to put cathodic protection in new structures. Not done a great deal outside of perhaps places like the Middle East, where they have very saline water and it's difficult to get sand even that's for concrete making that is free of salt. But generally speaking, they tend not to get used as much as they could be. Other things, discrete anodes. If you can imagine, you can drill a hole and you can insert something that is also going to act as an anode. You can work in 3 dimensions. You can make them longer, deeper, more close together, further apart, and really model the current that you're distributing for optimum effect. These are just some various. These are a bit old now, but the top one, top right, is a coated titanium. The middle one is titania, so it's titanium oxide. Works without any coating because it is already, as it were, oxidized titanium. Works very well. And then we've got a couple of coated titanium alternatives below that. In terms of applying it, this is the underneath of a tunnel deck. You can see the mesh is the coated titanium mesh. The little black dots are plastic fixings that hold it in place. The dark lines you can see are ribbons that are being used to distribute the current and also boost it in certain areas. That won't work on its own. It needs to be embedded in mortar, and what they tend to do there is use sprayed concrete. So it's a dry sprayed concrete. It goes over that. It protects the mesh. It acts as the electrolyte. It provides the environment in which you continue to operate. And that's proved to be a very, very effective system in infrastructure repair. On lighter structures, it's possible to use conductive coatings. This is a waffle slab in a car parking garage. It says conductive coating. You can't see the conductive coating. It's black. It's carbon based. It's painted white for obvious reasons. Not good lighting if you've got it black. Also, the coating on top protects it from moisture damage. There are wires that run along on the coating's been placed over that distribute the current. And in this case, on the ribs, which have got more steel in them, from the top of the deck, we've got 1, 2, 3 anodes, discrete anodes, rod anodes drilled in and linked by titanium wires, and the whole thing made good. So that's using different type. You can combine these as necessary to get the effect you want. That type of discrete anodes has also been very useful on historic buildings. We've got a lot of buildings from 1900, 1920, and not just in the UK, but worldwide, building closer to home in your own. Some of those old colonial buildings will have been built in the same way, a steel frame with probably a Portland stone or a similar stone finish. The steel frame starts to corrode. You can strip it, treat the steel frame, put it back, but you're just resetting the clock. If you can put and get anodes in there, you can cathodically protect that steel frame so it just stops corrode. That's it. And with a bit of thought and a bit of care, you can make sure all the wires are lost. You can either do it from the back, or in this case, you could do it from the front and then lose all the cabling into the joints. And you would never know it was there. There's a lot of buildings now that have got that way of protecting them. Just quickly going retro, galvanic anodes, they've become more widely available, generally based on zinc. Often like the ones you can see on the left there, the two there, they're used for things like tying on at the edge of repairs, and they just stop, they stop corrosion occurring in the area adjacent to the repair. Otherwise, that area has still got chlorides in and it will start to corrode. The zinc in there is in a special mortar that keeps it active, and it's very high alkalinity, stops the zinc from passivating, so it'll carry on rotting. It will only last a certain amount of time, but they can last 10, 15 years, which is often considered good enough. The gentleman on the right is doing a trial that's in Dubai, some much bigger versions of these, and that's been, dearie me, Shocking. I've not been speaking enough lately, obviously. Yes, you know, that's been used on in a seawater intake. They're, as I said before, they're often sold as, hey, these are great. You don't have to do anything. The flip side of that is there's not a lot you can do. You can monitor them. There are better monitoring systems. Really, all you can do is check it's working and see when it stops working. You can't really do anything about it other than that. But in many cases, it is a very good solution. And of course, you don't need a power supply. So in isolated small areas, it's perfect. In areas that are not difficult to access or may have concerns about the power supply being interrupted, they're a good solution. And you can even get a sticky bag zinc. Of course you can. I say sticky bag, it's actually a hydrogel adhesive with a activator in it, something that will keep the zinc busy. You've got to make separate connections that link the zinc through to the steel. You can see these plates. I think you might be able to see some couple of plates that go through with a nail into the steel. This was on a joint where there was about a day to do something. And so there's very little time to do much. Went in, threw as much of this stuff on as possible. And it's actually worked surprisingly well. Other areas where that type of system has been found to be useful, it's been on treating pre-stressed beams. Now, anybody who's done the theory on CP will know, they go, oh, you can't use cathodic protection on pre-stressing because you get hydrogen embrittlement. Well, it's true that some steels will be susceptible, not all steels, and usually the ones in these types of pre-stressed beams structures are not susceptible. That aside, overprotection is not a good thing. It can generate hydrogen. But if you use a galvanic system, it can't overprotect sufficiently to generate the hydrogen. So this is a very early trial. We're going for about 20 years now. That's and has been widened out. You can see the connection there. The whole of this, by the way, has been coated with a cementitious coating to hide the zinc, match it in better, and also protect it from its self-corrosion. Perfectly capable of using it. Sounds low tech, but when you think about it, it's real cutting edge. But it's cutting edge of a technology that, at this stage, is already getting on for 200 years old. And that's it. I hope that didn't overrun too much, but I just wanted to cover enough of it to make it relevant and hopefully interesting. And if there are any questions, if there's time, I'm happy to join in with any conversation. If there's questions later, we've got a couple of emails there, and I'm more than happy to respond to any questions that might come. So thank you very much, and you're back.
Thank you, Paul, for such an insightful and thoughtful session. So, as we conclude, I would like to take a moment to express my gratitude. So, if anyone has any questions, they can pop up, put the questions in the Q&A, and we have a couple of minutes to take a few of the questions. Anyone have any questions, can put up the questions.
Sir, I have one question regarding the surface modification of stainless steel bar. This steel was, could we use polymer coating over the surface of this steel bars, corrosion protection?
That interesting thought. Of course, it has been used, particularly in America, initially in the USA, in Florida, and subsequently in quite widely in the Emirates. The use of an epoxy coating. So they use fusion bonded epoxy coating onto the reinforcement. It sort of works, and I'll tell you why I say that. The problem with it is that for it to work really effectively, it has to be pretty well perfect coating. And of course, you've got to bend it, you've got to cut it, you've got to place it, and it tends to get damaged. There was a system that was briefly available that had a little galvanic anode that you've crimped onto the end of the bar. And the idea was that much as you would with a pipeline, you've got an epoxy coating, but you've got a bit of cathodic protection to make up for the defects in the coating. never really caught on. Some places do still require to use epoxy coating. The two downsides that have been identified with it are, firstly, the epoxy is marvelous except in one condition. If it's in warm, wet and chloride conditions, it softens. Now, unfortunately, the very place you want it to be working is usually warm, wet and chloride rich. And so the very time you want it to be an effective barrier is the time when it fails miserably, or can do. The second one is if you wish to put cathodic protection on afterwards, and most cathodic protection is applied retrospectively to reinforced concrete, it's an additional complication. It's not impossible. We've certainly done it, but you've got to break out more steel. You've got to make sure you've got connections to the steel that may otherwise be isolated because of the epoxy coating. And so it's a balancing thing. I know I can give you one example of where it worked incredibly well, and that was on the segments for a tunnel, a subsea tunnel, where the tunnel segments were made from reinforced concrete, and the cages, which are pre-formed, were epoxy coated. So they were epoxy coated using a much harder grade than normal. They were epoxy coated using a pipeline grade because the cages were already made. There was going to be no cutting, no bending. They could use a much better epoxy. They used that material on those precast units, and it worked. It has worked incredibly well. So I would say it's well worth considering on precast units where you can preform the reinforcement. It's less obviously a benefit when it comes to areas where you're going to be cutting and forming the reinforcement in situ. And there, you're probably better relying on good cover, good concrete, and the basic protective nature of the concrete and the alkalinity, with the prospect of at least being able to go back and apply cathodic protection relatively easily, should you wish to later.
Thank you, sir. Thank you so much.
My pleasure.
Stephen is asking that is there any what's about the use of CP concrete in India? How widespread is that? Stephen has joined our immediate past president.
Oh, right. Hello.
Yeah.
Yeah. Well, I am aware of systems that we've been involved with, but there must be much more, far, far more than I'm aware of. And for a start, there will be an awful lot in various pipeline applications. And certainly some of the applications I'm aware of are a pipeline, not necessarily oil and gas, because wherever there's a metallic pipeline, generally steel, sometimes things like ductile iron, there is often, if not immediately, then eventually a need or a benefit seen in using cathodic protection in order to protect it. So there is a lot. Could there be more? Very probably. And can it widen out its applications to more structures? Well, going by experience elsewhere, then I would be surprised if not. I think what you need is the engineers within the right sort of entrepreneurial attitude to see the possibilities. That's certainly how we benefited in the UK, in the US, in parts of mainland Europe, where there's some very, very, very smart people. Middle East, it's there, and it will be in India. It's just I can't give you an exact example of it.
One question is that they're asking, so if you're using stainless steel 3054 pipes in bare condition with CP requirement, and the soil is very cohesive, so can we use stainless steel in a bare condition with CP requirement in highly corrosive soil condition?
Well, you can. I mean, the thing is, one of the problems with stainless steel is, of course, it's 5 different families and 2,000 grades of each. So it's like it'd be like saying, and I'm not being rude here, because it's a problem with the education of engineers in many ways outside of very specific areas. Saying, can we use stainless steel would be like saying, who can run faster, an Englishman or an Indian? You know. It depends which one. And Can you use stainless steels? It depends which one. There's some very good performing stainless steels that will have a wide range of performance and are not necessarily as expensive as you might think. There's a whole body of duplex stainless steels which are capable of resisting much more, certainly with chloride as a good example of the sort of environment you might encounter, and are capable of doing much better than some of the more traditional grades that are considered to be good in chlorides, and yet may be no more expensive and frankly should be cheaper. Because they achieve it with less nickel. The cost of stainless steel is often the nickel, or at least it greatly influences it. Now, in the traditional grouping of them, you go, let's put more nickel in, it's got to be good. But it's not if you're having to pay for it. But there are duplex stainless steels that can be very effective. There are some, of course, some chemical environments that no metallic system will be comfortable in, and you're going to have to look at systems that use combinations of, say, material selection, protective coatings, and cathodic protection. So the material itself gives the performance probably for the resistance to what it's moving, the internal performance of the pipe, but externally you're relying heavily on a coating or a wrap or whatever. These can be pretty hefty wraps. And then you may be using cathodic protection just to protect those little defects that are inevitable in life, either during the time it was installed or just through in service as the coating starts to break down. So it's often as in all things in life, if you can work cooperatively, you'll get a better outcome in the end. And so can our corrosion protection systems.
Yeah. So
hello, Paul. Thank you so much for the nice presentation. I just want to have your views on the codal provisions, like what is there in UK, and what do you think should be the codal provisions with respect to the Indian scenario? How important are the codes while designing CP system? Yeah.
Well, I mean, the great thing about a lot of them now is that they are international. They're ISO. I mean, as India is a signatory to the ISO system, you have every, well, on the one hand, right, on the other hand, obligation to be using them. So if I think about, I'll start with reinforced concrete, but it's true for marine applications, type for pipeline applications. There are ISO codes that give. They're not a how to do it pamphlet. I mean, there are ISO codes on how to design a bridge. Yeah, I could read it and I could have a go, but it wouldn't be a very good bridge, and I'd probably be locked up when it collapsed. So it's got to be used by the right people. But those codes give the guidance that's required, and often the guidance isn't knowledge that isn't held by the people who are doing the design, but it gives the right for them to demand it off the client that they do this. The client, what would the client like? The client would like the simplest, cheapest system that involves no maintenance and they never have to look at again. If the code says no, it's got to be like this, there's got to be this much monitoring on it, you've got to check it this often, the quality, the competence, the certification level of the people who are doing the work has to be this high. The people who are just inspecting it has to be these people. It's there as much to protect, it's there to protect the client, to be honest, by making them get what they think they're asking for. But just stop it being shortcut. It stops the shortcut, which is where the failures occur, when people don't do the things they're supposed to do. So there's nothing necessarily highly clever in these documents, but what they do is they give you a good basis on which to carry the work out, and also something that other parties can look at and go, oh yeah, they do need to do that. I appreciate that now.
Yeah.
But the ISOs are there, and they're there to be used, and it doesn't matter if it's a jetty or it's a pipeline or it's reinforced concrete. The ISOs should be a good alternative. I mean, there are other standards that are recognised. Obviously, NACE we mentioned before. A lot of the standards still are NACE standards, and people often apply those. I think, and there will be local standards, of course, there will, but an awful lot of them these days. I think the movement these days is tending to move towards, let's all agree on the ISO. All we've got to do is get the ISO, get our standard front sheet, staple it on the front and go, there we are. That is
Yeah.
now our
Uh,
standard. You go, it's an ISO.
uh,
Yeah, good, eh? It means that we're not alone here.
Okay. Yeah. Thank you.
It's a pleasure.
Yeah.
Thank
Thank you, Paul. And also thank you to all attendees for joining us today. And we hope to see you in a future events. Before we end, I think I'd just quickly like to invite Shagufta to just tell you about how to become the ICOR member. So, Shagufta, if you could just quickly share something about the membership.
Yeah, sure. Sure. So, hello once again. First, let me tell you benefits of membership. So, Institute of Corrosion provide 12 months young engineer program for young professionals, and which give a lot of opportunity for networking and career development. And institute also provide chartership, two kind of chartership, that is uh, charter scientist and chartered engineer. And Institute of Corrosion give you a lot of networking opportunities, so you can build a sense of being a part, big part, you building a sense of community, being a part of something bigger, and sharing experience, knowledge, and best practices. Then advocacy, working together to convince other of the importance of what we do. And you understand commercial value of who and what you know as a result of membership. And of course, there is a lot of fun in joining this big organization and big community of corrosion professional. Then you have financial benefits also, like you get discount on conference fees, including EuroCore and major UK conferences. Then it's free for the membership is free for students. And you get free subscription of corrosion management journal, that is institute journal. And visibility, yes. uh, you grow personal reputation, association with an organization that stand for excellence in corrosion science and engineering. And it's very easy to become a member, but you get a lot of benefits. Become affiliate member, you can join online. And once you are affiliate member, you can apply for your this professional membership. An institute provide three kind of professional membership, that is technician and professional membership and fellow. uh, and you get designation of TICOR, MICOR, and FICOR based on your work experience. Right. The institute has its own journal, Corrosion Management. It's published bi-monthly, and it's circulated among all the subscriber. And this journal publishes high quality technical articles, industry news about innovative products, and innovative ideas. And if you want to contribute any technical article, you can send your abstract and your bio to editor. This is email ID. Okay, thank you very much. Arpit, now you can continue.
Yeah. Thank you, Shagufta. So, as Shagufta mentioned, it's quite easy. If you have any questions about the membership and would like to join us, you may please email it to us. You already have my email address on the webinar flyer we just shared. And once again, I would like to conclude by thanking Paul again for its insightful session today and to be the first technical session, to host the first technical session with us. Thank you, Paul.
Many thanks, and thank you for the honour. Frankly, it's very kind, very good of you to trust me.
Thank you. Yeah. Thank you, everyone, for joining us.